Okay, this is a nice article that is kind of a news type report on the science of cool innovations to protect cities from dangerous heat. Well, we know that urban centers have heat island effect and they are contributing disproportionately more to climate change and are being affected by lots of specific urban problems during climate change as well. And we know that as warming happens and as economies grow in China and India, more and more air conditioners are being bought, and that will continue. And of course, that uses energy, but also leaks material like HFCs, HCFCs, which are now very potent greenhouse gases. And there is a race on to replace those coolants with other materials which are not harmful to the planet. And we came from CFCs to HCFCs, HFCs, because we thought they don't affect the ozone hole, but instead they ended up being greenhouse gases. So now we are moving to something else. So poor countries have to do that as well. But there is another way to do this, although the scalability and practical applications are not clear yet, where you use materials for roofs which are facing up or sideways, let's say, or walls which are also facing the ground, so they can put heat back to the ground, which is what causes things like urban heat island. So people are trying to use material properties to reflect sunlight, which is the more obvious thing, but also try to produce the outgoing long wave energy after they get heated in specific bands that can be allowed to go directly to space, because the atmosphere traps outgoing long wave but not at all wavelengths. And then there are also materials which are using electric fields to rearrange the atoms in ceramics, for example, to cool or heat based on the time of the day or based on the ambient temperature. And there are also materials which are acting like superconductors when they are cool and becoming metallic when they are warm, so they can absorb heat in one case and reflect heat in another case. So seasonally they can be used. So lots of exciting innovations, but all are in kind of a small scale application or still in the lab. So that's kind of the summary. So let's read some main points here. From supercool materials that send heat into space to shape-shifting materials that can selectively fend off the heat, scientists are finding new strategies to reduce urban temperatures. The results are good, but scalability is still to be tested. Hundreds of air conditioning units adorn an apartment building in Nanjing, and in India you get nice pictures of low income neighborhoods also adorned with air conditioners, because people need this, not just a luxury item anymore, it's a necessity. Plus the easiest adaptation to warming is to buy an air conditioner, right? So the consequences are what we have to worry about. It's time to brace for record-breaking heat. Last year was the hottest year on record, 2023, and 2024 is shaping up to be even more extreme. Obviously, we have had warm months to the middle of 2024, and now we are going down, as should happen with natural variability. The La Nina that was supposed to come and cool things hasn't really come yet, and so on. And there are numbers of deaths that are attributed to heat waves or heat stress as well. 500,000 people each year, according to one estimate. There are always uncertainties about these. So advances in materials, working hard to develop innovative ways to cool cities and slash electricity use in warming world, produce high efficiency air conditioners in one approach, to special materials that keep surfaces colder than their surroundings without using electricity on the other approach. So ACs are not going to go away anytime soon, so we have to make them more efficient and transition the coolants to environmentally safe materials as well. So what can the innovative cool materials can do. So there is a terminology of cool material and super cool material. Cool materials are basically relying on reflecting sunlight very efficiently and staying at a cooler temperature, whereas super cool materials also emit in wavelengths where the thermal energy can escape to space, and if the material is cool, surface is cool, then the air that is in touch also gets cooler, so you can produce larger scale cooling for a city, let's say, in theory, right? If you deploy them in large enough scales, then it can happen. Plus, remember that there are always just simple approaches like coating the roof with white paint or lighter material to reflect sunlight. And despite this simple technology, many roofs in Arizona are still dark materials, which actually increase the demand for cooling and energy, of course. So you have to worry about materials that are recyclable or biodegradable and so on as well, right? Researching refrigeration, then, in most air conditioners and refrigerators, a fluid is compressed to transfer heat from inside the room or appliance to outside, but this process emits greenhouse gases and guzzles energy. Globally, air conditioners and electric fans consume about 20% of the electricity used in buildings, according to the International Energy Agency, and the agency predicts that the amount of energy required for air conditioning around the globe will surge threefold by 2050. Okay, the amount of energy required for air conditioning will surge if we don't, make them much more efficient and also deploy materials that work without extra energy requirements, right? With that in mind, many researchers are working to reduce the amount of energy that air conditioners consume. One potential solution emerged last year when a team of researchers developed a technology that might make appliances work much more efficiently, and it has the added benefit of not relying on environmentally damaging liquid coolants. So you can go follow up on this reference too in the paper that I'm not going to go into. So jumping ahead to some of the researchers, Emmanuel Defay, a researcher at the Luxembourg Institute of Science and Technology in Bellevaux, and his colleagues built a device that relies on electrocaloric cooling. In this process, an electric field is applied to change the position of atoms in an insulating ceramic. Ceramic is an insulating material, but you can use electric field to move atoms. What happens? Because the field constrains the atoms' movements, their vibrations increase and are converted into heat, raising the temperature of the material. The fluid carries the heat away to the outside. Once the heat has been removed, the field is shut off and the atoms in the ceramic can move more freely. That causes their vibrations to decrease and the ceramic's temperature drops, a change that can be used for cooling purposes. So material is the same, but you are using electric field to rearrange materials to produce more thermal energy than otherwise, or cool it more than otherwise. But you are using energy here. So the life cycle analysis has to work even at large scales, and how it will be done in practical implementations is also not exactly clear. Now moving to game-changing materials. Other components known as supercool materials might be able to lower temperatures below ambient conditions without power. This is important. All materials reflect some portion of the sunlight that hits them, and all emit energy as heat, the blackbody radiation that we talk about. But supercool materials do both extremely well, reflecting most of their incident solar radiation and emitting a lot of their thermal radiation, so their absorptivity and emissivity are close to 1. That makes them cooler than their surrounding temperature. These materials are potentially a game changer, says David Saylor, director of the School of Geographical Sciences and Urban Planning at Arizona State University in Tempe, who doesn't develop these technologies but studies how they could be used in urban environments. Not only can they help to cool a building, thus reducing the demand for air conditioning, but they can also cool the outside air. If a surface is always cooler than the air, then the surface is always taking heat out of the air as the air flows over it, Saylor says. So it's actively cooling the urban atmosphere. So sensible heat works when the air is blowing nicely, dependent on wind speed and temperature difference between the material and the air that's flowing. The first supercool material was designed in 2014 when Ashwath Raman, material scientist now at UCLA, was conducting research at Stanford University, also in California. University of California, LA is UCLA. He and his colleagues created a cooling surface that was highly reflective at the visible wavelengths where the sun's radiation peaks and emissive in the mid-infrared. The latter is key. The atmosphere traps most of the infrared radiation emitted as heat by objects on Earth's surface, but a specific band of infrared with wavelengths of 8 to 13 micrometers passes straight through the atmosphere and disappears into space, so it's very efficient if you emit thermal energy in those bands. Supercool materials exploit that infrared window. Mounted on a roof, Raman's technology which was made of 7 alternating layers of silicon dioxide and hafnium dioxide, stayed 5 degrees C cooler than the ambient air temperature. That's significant. And scientists are continuing to push them further. This I'm jumping ahead. In July, researchers in Sichuan University in Chengdu, China, a beautiful city, reported that they had freeze-dried a solution of commercially obtained salmon sperm DNA and gelatin to create a supercool aerogel. When placed outside, the aerogel cooled the surfaces up to 16 degrees centigrade below the ambient air temperature. That sounds incredibly high, but biomimetic materials are now being created for all kinds of applications. Xianhu Liu, a material scientist at Zhengzhou University in China who was not involved in the study, is particularly excited that the material uses less energy and reduces pollutants compared to other supercool materials that use additives such as metal oxide nanoparticles. The fact that this work used biomass materials also means it's biodegradable. It's a rare combination of sustainability and energy efficiency, Liu says, but Raman doubts the accuracy of the study's results. 16 degrees C cooling does sound a little off. The team measured an air temperature 20 to 30 degrees C higher than that reported by weather stations for the day and location. It seems likely that the temperature sensor was exposed to the sun and heated up, so their results were maybe a little higher than what actually happened, but I'm sure that will be tested again. Cool surfaces. In his own research, Raman has moved from supercool materials to a category called cool materials, which are typically engineered to reflect most of their incident solar radiation, but not necessarily there to emit most of their thermal radiation. You don't need to do this fancy thing in the infrared, you just need to make it really solar reflective, he says. That's because most materials will still emit heat across the entire infrared spectrum and will reach temperatures slightly below those of ambient air if they are reflective enough. So if you just don't absorb and reflect, you will be cooler without worrying about doing band passing of thermal energy. Raman has also been working on another type of material for vertical surfaces such as building facades. This is a difficult application because walls face both the sky and the ground, so they absorb heat from the earth during the summer and lose heat to it during the winter. So buildings are warmer, they will provide heat to the ground during winter, but during summer when the surfaces reflect thermal energy, the sides can absorb that thermal energy. Raman's team found a potential solution to this. In June, the researchers reported a physical mechanism that relies on a special material to cool or warm walls depending on the season. The coating achieves this by selectively losing heat towards the sky and gaining much less heat from the ground in summer. And in winter, it loses less heat to the ground than a conventional wall does. To boot, the team has found that many low-cost materials have this unique property, including the polypropylene bags used for crisps or potato chips. So we are really looking everywhere, and now it's found that the material some kind of a salt or a chemical that's used in some of the chips is also useful for some medicinal purposes, I think. You can read it up. The discovery could be a boon for places that don't have air conditioning and could improve thermal comfort and even human health, he says. I don't want to advance the perception, especially among architects and engineers, that this is some far away thing, Raman says. I want them to realize there is a lot of things we can do right away. Some more reading material here. Other researchers are also working on this problem. Report this month by Yuan Wang, a material scientist at Columbia University in New York, my alma mater, and his colleagues describes the work in which they applied a super cool paint to a corrugated wall, and so they only applied to the sun-facing side of the corrugated roof versus the dark side, and so on. But basically, these are again using approaches like this, where researchers applied special paint to a car park. So here a special paint is applied, and this is the regular material, and you can see that the infrared image shows the area was cooler than the surroundings where the paint was not applied. So researchers applied special paint to a car park, left the pale area in Arizona, sorry I said it wrong, the pale area here in this left panel, and here it has cooler temperatures. So when you have higher thermal energy, you are looking whiter. Imagine a blacksmith who's putting an iron rod in the fire. If it's still looking darkish, then it's hot, but not hot enough to reflect energy. But if you keep heating it, it gets whiter at higher temperatures and reflects more of the thermal energy. Okay, so the trick allows materials to stay cool or warm depending on the external temperatures. So let's read this a little bit more here. So I'll jump ahead in the reading here. Other technologies are attempting to cool cities from the ground up. Last September, a team at the Arizona State University Tempe, led by Sailor, partnered with a US company that managed a large shopping center to deploy and test reflective cool pavement, which is the result we looked at here. These are again to be tested, and the amount of cooling here was 0.8 degrees C compared. So the difference between the warm side and the cool side was 0.8 degrees C. Is that enough? Well, if you do it on a large scale, then the energy demand will be significantly lower. Okay, so there are other materials called shape shifting materials. Muhammad Taha, an engineer at the University of Melbourne in Australia, and their teams are taking a different approach to cool homes and buildings. Early in 2023, the team described phase-changing inks consisting of suspended nanoparticles that change phase depending on the temperature, shifting from a superconductor at cool temperatures to a metal at hotter temperatures. That trick allows materials to stay cool or warm depending on the external temperature. In short, when the material heats up and becomes a metal, it adopts a linear structure that can reflect extra heat. When it cools and becomes a superconductor, the material adopts in an insulating zigzag structure that allows the heat in. So you want the heat to be trapped for winter temperatures and to be lost as thermal energy for warm temperatures. So in the future, Taha hopes to apply this ink to a window coating. So applications are yet pending. Scalability is yet not clear. Life cycle analysis is not yet clear, and so on. Keeping all those caveats in mind, how do you go from lab to cities? It's not yet clear which of these cooling technologies are likely to have big impact in the future. Many have not left the lab, and others have been deployed only in small scale projects. For that reason, Saylor argues that researchers need to evaluate all new materials carefully before moving forward. It's really important that we in the science community, and I take this one as one of my responsibilities in evaluating these technologies, focus not just on their strengths but also on their weaknesses, right? The cool pavement, for example, has a potential drawback in that it reflects radiation upward. Someone on that pavement, when the sun is high in the sky, will feel the reflected radiation from below in addition to that from above. So person is getting direct sun and also from below reflected. Someone is going to feel that for sure. He suggests that coring would be less suitable in areas such as playgrounds where individuals might spend a lot of time on the surface than surface in the middle of the day. A better option would be to use it on street pedestrian crossings where individuals spend mere seconds running across. There are always questions about there are also questions about how well supercool materials will work in a wide variety of climates. If it's cloudy or humid, for example, such materials might be less effective. That's because water vapor traps the infrared radiation, stopping it from escaping to space. So lab conditions have to be tested in the real world for real world conditions. Raman, however, argues that supercool materials can still perform well in these climates, even if they can't cool the air temperature surface. Even if they can't cool the air temperature sufficiently, he says they won't heat it up either. Wow. People who do these things are always kind of very gung-ho about it, but practical applications will give us data on these details. Another unknown is whether consumers will embrace the idea. Even the simple measures of replacing old roofs with lighter reflective ones has not been widely adopted. As part of his work, Saylor routinely takes an infrared camera up in a helicopter over Phoenix, and is always amazed by the number of dark rooftops despite the benefits of cooler, lighter roofs. I have this experience at home as well, telling my family members to paint the terrace white, but they said, meh. Nonetheless, several cities are testing and deploying various mitigation technologies. LA, for example, has been adding cool pavements with the goal of increasing cool surfaces there by 30% by 2045. Finally, I think this is the last slide. Mateos Santamouris, a physicist at the University of New South Wales in Sydney, Australia, and his team have applied similar materials in more than 300 large-scale mitigation projects across the world. In January, his group detailed a multifaceted strategy to cool Riyadh by up to 4.5 degrees C. This is really the champion of the mitigation projects, Santamouris says. The recommended approach which Riyadh has started adopting includes retrofitting buildings with both cool and supercool materials and doubling the number of irrigated trees for shade. Although the approach includes a suite of solutions, Santamouris' team calculated that the addition of supercool materials will have the biggest impact. The market is increasing tremendously, Santamouris says. About these materials, there are more and more industrial producers around the world. I think that this is the future. The good thing about a place like Riyadh is it's a rich country, oil wealth is tremendous, so they can try large-scale implementations and provide data for the rest of the world to see whether implementing them, let alone retrofitting old buildings with these cool and supercool materials, is really cost-effective in terms of reducing energy demand, cooling enough without energy, and so on and so forth. Okay, I think I say so on and so forth quite often as well, but let's leave this here. And the next topic will be, I keep saying the next topic in podcasts, and sometimes I read the next topic and say, that's not interesting enough to report. Okay, so yes, this may be interesting enough. This is on floating homes. With sea level rise and storms and coastal erosion and so on, can we just build floating homes like the water world to make some living spaces in coastal regions as well? Okay, so let's come back and read that a little bit as well. Okay, see you in the next podcast.